All right, 2.7 is over dilations. We've talked about 3 types of congruent transformations. We talked about translation, reflection, and rotation. We only have 1 type of similar transformation, meaning that when we transform this shape, it's not going to be the same size, but it will still be the same shape. That's what similar means. So a dilation is a transformation in which the figure is made smaller or larger. I had to think about that for a second. Smaller or larger with respect to a point called the center of dilation. I was thinking of the words reduced and enlarged, which would not have grammatically made sense in that sentence. So we'll just go smaller and larger, but that's what we actually call it, reduced or enlarged. With respect to a point called the center of dilation, this point does not have to be the origin, but often it is. So you've heard about dilated eyes, especially with all the concussion protocol stuff going on. They will say, oh, your eye is dilated. Well, when you go to the eye doctor, they'll dilate your eyes as well. And so when you dilate your eyes, so basically that's going to change your pupil size. It doesn't change the shape of your pupils. Your pupils are still circular. Be weird if they went to triangle shaped or something like that. But the reason your pupils shrink or enlarge, it has to do with how much light they're experiencing. So if you've ever been in a dark room and then immediately gone inside, you might get this pain in your head, like or maybe you're driving in the car and there's snow all over the ground and it's that sunlight's reflecting into your eyes. You see people wear sunglasses in winter because of that. So what happens is when it's very bright out, your pupils are going to dilate, they're going to shrink down because they don't need to intake all that light. Whereas when you're in a dark room, especially when you walk into a dark room, you can't see anything. And then eventually you start seeing outlines of things. And that's because your pupils are enlarging and they're trying to absorb as much as they can because there's not very too much light. So when your pupils are like this and you walk outside in the bright, that's why you get that headache, because they're taking all that light in. They're like, oh gosh, that hurts. So yeah, your pupils dilate. That's something we'd probably have heard a lot. And shapes can also dilate as well. They're not going to change shape, but they will change size today. Tell whether the blue figure is a dilation of the red figure. Why or why not? Why don't we change it with this? Is it a dilation or is it one of the other 3 transformations we've talked about? Example A. Is the blue triangle a dilated image of the red triangle? Owen? It's exactly the same. You're right. So it's a congruent transformation. So the answer is no here. It's not a dilation. And then what kind of transformation do you think it is then? Would you say it's been translated, reflected, or rotated? Just translated. Yeah, it's just been translated. It's just been moved. Okay, just been moved. What about example B? Is the blue triangle a dilation of the red triangle, Lucy? Yeah. Yes, it is. This one is a dilation. In fact, I'll show you where the center of dilation is. And you can do it too if you draw these lines. So if you draw a line that connects the top vertice of both triangles, I'm going to draw it all the way out here. Do the same thing with the middle vertice. And then the bottom one, if I can get it to line up properly. Maybe not. About as close as I'm going to get it. You can see that they all intersect around the same spot. And so this intersection point right here is called the center of dilation. So that was the point at which it was dilated from. And since we're going from red to blue, we would say that this image, this blue triangle, was a reduced version of the original. Example C. Is that a dilation, Christian? No. What would you say it is? Reflection. Yep, good job. That's a reflection across this vertical line. We can assume it's the y-axis, although it doesn't have to be, but it was reflected across that vertical line right there. And then D, is that square, blue square, been dilated or something else, Xander?
Yes.
That one is a dilation. And if you want to find the center of dilation for that one, you have to draw 4 lines because it has 4 sides. This one's kind of cool. How many of you guys in art class, how many have you taken art class so far? You guys had to do the perspective drawing with the like the road it's going to, you know what I mean? I don't know. I don't know the correct term. You might remember something like this. Is it perspective? Okay. I took art class too, but I took it in high school and got a C. So I'm probably not the one to tell you about perspective drawings. Well, it's a good question. Every time she'd walk by, she'd pick up my pencil and start fixing my picture. So she was giving herself a C at that point. So she did all the work. It's probably not a good excuse. If I extend these lines, this is not going to be a very good one because I'm losing accuracy right now. But the center of dilation is extremely far away. Again, it's not accurate because I'm just adding on to these lines, but somewhere in that area there. And so again, it kind of looks like if I were to chop it off right here, it looks like a rectangular prism. That's how you would draw that. Yes.
Is that basically what a telescope is? Just a bunch of glass dilated sphere?
So with a lens like that, there's more science to it than that. I mean, yes, right. When you look at a planet through a telescope and it's that big, it's not really that big, although the shape is the same. So yes, in a sense, it has been dilated. There's a lot more science that goes into the lens of, because a lens is just a sphere that's been chopped off, right? So, or actually it could be a section of a cone as well. So I don't know. I'm just going to leave it at that. I don't know exactly how all those, it's series of lenses and mirrors and a lot more stuff than I'm over my head. Let's just say that.
Okay.
Sorry, I don't have a good answer for you. All right, moving on. The 2 triangles are similar. So they must be dilations of each other. Compare the coordinates of the red triangle with the coordinates of the blue triangle. And then we're going to do the coordinates of the blue triangle to the red triangle as well. So from red to blue, we'll do that first. I need to know what the red coordinates are. Julia, will you tell me what the point A coordinates are?
-6.
Good job. Okay, Emerson, I need point B. Maddox, I'll call on you for point C.
6, 6.
6, 6. Okay. Maddox, what you got for C?
3 -6.
3, -6. Okay. And then for the blue triangle coordinates, Q, R, and S, Carter, I'm going to give you Q. Christian, I'm going to give you R, and Garrett, I'm going to give you S. Go ahead when you're ready, Carter. Are you in the notes, Carter?
Yeah.
Okay. Tell me where point Q is located.
Oh, 1, 1. -2, 1.
-2, 1. Okay. Christian? 2, 2. Are you a ballerina or something? It's a bad joke. Garrett, what do you got? 1, -2. Okay. So I want you to compare the coordinates of the red triangle to the blue triangle. We'll assume that to keep our red to blue consistency, that the red triangle was the original one right now, and the blue triangle was the image. Was the triangle enlarged or reduced? Sky? It was reduced. Okay, I'm going to put an R for reduce. And if you look at the coordinates, Sky, what did they reduce it by? To go from A to Q or from B to R, what did they reduce the coordinates by? Dividing by 3, that's right. Now, when we're talking about dilations, we will never use the word divide. Instead, we're always going to think of it in terms of multiplying. So Sky, dividing by 3 would be the same as multiplying by what fraction? 1/3. Okay, so I'm going to put R, and then we're going to say it was reduced by 1/3. You're not wrong, Sky. You could have divided by 3. It's just when we write these, we write it in as a sense of as a coefficient Like a coefficient is a number that's being multiplied to another number. So that's what we need to think of. What number would be multiplied? So if it's being divided, think of it as a fraction. What about if I told you the blue triangle was the original and the red triangle was the image? Obviously, it was enlarged by a scale factor of what, Owen? By 3, the exact opposite, or you might say the reciprocal. So if I went from blue to red, it would have been, I still want to use purple, should have been enlarged by a scale factor of 3. In a dilation, the image is similar to the original figure. The ratio of the corresponding side lengths is called the scale factor. You don't actually have to know the side lengths to figure out what the scale factor is. You can do what Sky and Owen did, and you can look at the coordinates. You look at the coordinates here. Now, this is in respect to the origin. These shapes were dilated in respect to the origin. What I mean by that is if you draw a line through A and Q, if you draw a line through B and R, and if you draw a line through C and S, you can see the origin was our center of dilation. Okay, if the origin is not your center of dilation, you're not going to be able to just use the coordinates, but we can here because we're starting at 0. So she noticed that -6 goes to -2, 6 goes to 2, and 3 goes to 1. It's being, she said, divided by 3, or we would say times by 1/3. And then Owen reversed that and said, well, if you go the other way, it's just being times by 3. That's right. Okay, so that's the ratio. If I actually told you what these side lengths were, let's say I told you, and we could find out if we knew how to use the Pythagorean theorem, but we don't know yet. Some of you might, but I haven't taught it to you yet. Let's just say that this one here was 3.5. Well, if that's 3.5, I would take 3.5. I would times it by 3 because we said the red triangle is 3 times bigger, and that would make this side 10.5. And if I write 10.5 over 3.5 and reduce it, I'll get 3 over 1. So my ratio is going to be 3, whether I'm looking at the side lengths or easier, just look at the coordinates if it's being dilated with respect to the origin. To dilate a figure with respect to the origin, multiply, not divide. Multiply the coordinates of each vertex by the scale factor. We're going to call it K. So your arrow notation today, and there are 4 problems on tonight's homework that you have to show arrow notation on. I believe it's 23, 24, 25, and 26. And you'll know when you get there because it's going to give you 2 transformations and it's going to say, here's your coordinates. Tell me what the double prime coordinates are. So you'll want to show arrow notation there. But when you get to the dilation part, let's say it's being dilated by 2, you would write 2x, 2, 2y, because you're multiplying both x and y by 2. If you're reducing it by 2, or by half is what we would say, then you'd put 1/2 x and 1/2 y. So if your scale factor is greater than 1, you're going to enlarge your shape. If your scale factor is between 0 and 1, you're going to reduce your shape. So that makes a pretty obvious question. What happens if your scale factor is 1? What happens when you times all the coordinates by 1? Xander?
Still 1.
Well, that's not still 1.
Or it's still the same.
It's still the same. Yeah, so if you times all the coordinates by 1, what happened to your shape?
It's the same.
It's the same. Nothing happened to it. Exactly. So there was no transformation done then, right? What happens if you times all the coordinates by 0?
Nothing.
Yeah, so they all become 0, 0. Now you have no shape. Right? Now, we're not going to times by negative, because if you multiply by a negative, you are going to start reflecting your shape. Remember when we said you take the opposite of the x, opposite of the y, that's going to reflect it over one of the axes. So if you were to say, for example, I'm going to times it by -2, then what you would actually say is I'm going to enlarge it by 2 and reflect over a certain axis. And if you're timesing both coordinates by -2, what one transformation times both coordinates by negative? Remember, Lizzie? 180-degree rotation. Exactly. So you'd be doing an enlargement and a 180-degree rotation. Exactly. So it's not to say you can't times by negative. It just means that now you're going to start rotating / reflecting it. And so we're just going to stick with keeping those separate for now. Okay. So tell me what would happen to the shape. Is it going to be enlarged E or reduced R if you times by a scale factor of 2, Jacoby? Be enlarged, yeah, twice the side lengths would each be doubled. Exactly. For what about B? What if my scale factor was 2/5, Jimmy? Is it going to be enlarged or reduced? Yeah, be reduced. That 2/5 is between 0 and 1. So any fraction that's a proper fraction is going to reduce it. What about 1/3, Seth? It would reduce it. Yeah, be the same as dividing by 3, which is what Sky said earlier. What if I times by 1, Lucy? It'll stay the same. So I'm just going to put a line through that. Yeah, nothing's going to happen there. We just mentioned that. Seth, what if I times by 0.5? Or Seth, sorry, Seth, you just did that one. Jace, what if I did 0.5? What would happen? It would reduce it. Okay. And Christian, what about 5/4? It would enlarge it. Yeah, because that's an improper fraction. It's actually the same as 1 1/4 or 1.25. It's going to enlarge it. Okay. All right. So there's your arrow notation. This is what I'm going to add to your transformations key that I'll send out tomorrow. It's just this simple part right here. If you times by something bigger than 1, it's going to enlarge. And if you times by something between 0 and 1, it's going to reduce. By the way, that's true for anything. I remember when I was in school, I was like shocked that when you multiplied 2 numbers together, they didn't always get bigger. Because you learn from an early age, you multiply, you're thinking factors that are larger, right? But if you multiply by 0.7, it shrinks. Or here's another example. If you multiply by 0.5, it shrinks in half, even though you're multiplying. The same happens with division, by the way. When you divide by big numbers, you get a small number. When you divide by small numbers, you get a big number. For example, if I told you to take $3 and divide it by 0.1, I'm asking you how many dimes there are in $3. How many dimes are there in $3? Lizzie? Not 300, that's how many pennies? 30. Yeah, see how the number's bigger? It got bigger. Even though I was dividing, I divided by something really small. So it goes in there a lot. Right? So again, between 0 and 1 makes a difference. Okay, moving on to, we're actually going to do it on the coordinate plane now. Dilate triangle M and P by the given scale factor with respect to the origin. We're going to times everything by 1.5. You could use your calculator on here if you need to. Deegan, tell me what 2 times 1.5 and what 3 times 1.5 is. So you're doing M prime. Connor, you're going to do N prime. And Brady, you're going to do P prime. What do you got, Deegan? 4.5. Okay. Connor, what'd you get? 6 and negative 1.5. Brady, what'd you get? 1.5. Okay. So we're just going to do our best here when we're trying to estimate where those half marks are. Oh, we got 6 minutes. Okay. So M prime is going to be at 3, 4.5, which is going to put me somewhere here. That's going to be M prime. And N prime is going to put us at 6, negative 1.5, somewhere in that area. And P prime is going to put us at 1.5, negative 4.5. Oh boy, 1.5, negative 4.5 puts us right in the center of that square. Then connect, connect, and connect. And I won't do it just because we're low on time, but if I draw a line through M prime and M, N prime and N, and P prime and P, they should all meet at the origin because I'm dilating in respect to the origin. I'll leave that up there if you're still finishing. We'll move on to example B. Jacoby, I'm gonna have you multiply by a half for M prime. Martin, I'm gonna have you do N prime. And Carson, I'm gonna have you do P prime. So whenever you're ready, Jacoby, I think I called on you first. 1 and 1.5, okay? Martin? 2 and -1/2, which I'll just write it as a decimal since that's what I've been doing. You don't have to. And then Carson? That's right. So we'll try to plot these now. So M prime, now I'm timesing by a half, so I'm expecting the triangle to be reduced. Keep that in mind. So M is now 1, 1.5. That's my new M prime point. N prime is 2, -1/2. And then my P prime is 1/2, -1/2, 1/2, negative, wait, -1.5. Okay, so somewhere in that area. P prime. And I have a new triangle that has been reduced. Now, what's interesting here, and we'll talk about this more tomorrow, even though all of the side lengths have been reduced in half, it doesn't reduce the area in half. This triangle is not half of the other triangle, because that trapezoid would be actually bigger than that triangle there. Okay, so it doesn't reduce the area in half. It just reduces the side lengths in half. So if it reduces the side lengths in half, it does reduce the perimeter by half, but not the area. Because how many dimensions is the area in?
3.
That's volume.
2.
2 dimensions. Well, that's a big part of tomorrow's lesson. Perimeter is 1-dimensional, but area is 2-dimensional. And then Friday, area is 2-dimensional, but volume is 3-dimensional. And so that adds another layer. It's like Inception, it's a dream within a dream, within a dream. No, okay. Carson.
So by stuff, would like you be able to tell what the area is? Like, would it
You,
vary by a
yes,
certain amount?
yes, and we'll be able to do that tomorrow. Yes. All right, identify the scale factor of each dilation. So I want you to look at, I don't know, look at A and A prime, B and B prime. We're going from red to blue. I know that because the prime units are with the blue triangle. What is the scale factor here? What did they multiply all the coordinates by, Xander?
Enlarged by 3.
Yeah, they enlarged it by 3. So I'm just going to put 3 because from now on, if we say that they're reducing it, we'll just put it as a fraction. Okay. Yeah. So they've been enlarged by 3. So K equals 3. That doesn't mean the area is 3 times bigger. If I could, I will. I'll draw that triangle real quick. Can I only fit 3 of these triangles in the big triangle? I can fit a lot of, I can fit, several of those in the big triangle. Okay. Here's a way of thinking about it. If this side is 3 times longer, and this side's 3 times longer, and you do base times height, 3 times 3 is 9. This triangle's 9 times bigger.
Whoa.
So a dilation of 3 makes the area 9 times bigger. Because remember we said areas in 2 dimensions. What's 3 squared?
9.
That's right. It's tomorrow's lesson. Okay, here we have a red rectangle and a blue rectangle. What are they dilating the red rectangle by, Maddox? By 1/2. So K is equal to 1/2. That doesn't mean the area of the blue rectangle is only half. I can fit 1, 2, 3, 4. So the area is 1/4 of the size. What's 1/2 squared? 1/4. Area is in 2 dimensions. The perimeter is half the size, but the area is 1/4 of the size. Interesting. Volume would be to the what power then? 3rd power. That's Friday. All right, you guys can leave. We'll finish these notes tomorrow. Have a great day. Remember, 2.5 is due tomorrow.